Moving on from the simple linear growth model, we'll discuss now exponential growth. In linear growth, the rate of change of our function was constant. Here, the rate of change is ever increasing. What we know is that the time in which it takes our growth to double or triple or so on, this is constant. So we grow at a much more rapid rate than we did with linear growth. So how do we analyze such things? Well, an exponential model at its heart looks something like f of x equals a to the x, perhaps times some constant. So for example, f of x equals 100 times 3 to the x. This would essentially say, well, I start with 100 of something, and then every unit of x, I triple. So at x equals 0, I have 100, then 300, then 900, and so on. So we're trying to model phenomena that have this type of growth. So in order to solve equations related to these growths, we just want to remember our formulation of inverses of exponentials in terms of logarithms. That the logarithm is defined in some ways to be the inverse function of the exponential. So when I have questions related to exponential models, logarithms are an important tool for solving these problems. So just to review our exponential rules, we've already seen this in submodule 1.1, but recall that addition in the exponent becomes multiplication outside, and iterated exponentiation becomes exponentiation by the multiplied exponents. These are sort of the most important two. But it's good if we're going to talk about exponential models to be really ready with the properties of these systems. So a little bit of plotting never hurt anyone. So here's a plot of y equals 2 to the x. So notice that for small values of x, I'm tending towards 0. Right? So one way of writing this, which is very calculus-oriented, is that the limit as x goes to minus infinity of 2 to the x equals 0. That is, for sort of very negative numbers, this plot is tending towards 0. Whereas for very large inputs, it blows up to infinity. So here we're having blow up to infinity. To write this in sort of a style reminiscent of calculus, we'd say this. So the exponential model in this case can be thought of as, for very negative values of x, we're going to 0. For very large values of x, we're blowing up to infinity. And we can also reflect this plot and look at the function f of x equals 2 to the minus x, in which case things are reversed. As x runs off to minus infinity, we blow up. But for positive values of x, I'm going towards 0. So this is the exponential decay model. And the key point is that I have a negative sign in that exponent. Instead of getting bigger with bigger inputs, I get smaller with bigger inputs. So some real-world phenomena in which exponential decay is very reasonable, a lot of them come from chemistry. For example, the half-life of certain chemical isotopes are often governed by exponential decay laws. So let's look at an example. So suppose you have a population of javelinas, which are these little kind of southwestern pig-like creatures. And what I know about them is they double, their population doubles in size every 16 months. So after 16 months, however many I had, I now have that many times 2. Suppose that there are 100 to start. So I have 100 at the beginning. After 16 months, I have 200, then 400, and so on. And we can ask some questions about this model. First, we want to actually write the model down. Write a function for the population after a given time. Then we'll ask, how many javelinas are there after 6 years? And then the most interesting question, how long until there are 1,000 javelinas? So let's do A first. So I'll write the function for the population size as a function of time. So I know they double every 16 months. So if I divide by 16 here, when t is equal to 16, I'll get 2. When t is equal to 32, I'll get 2 squared, and so on. And then I start with 100, so I'll multiply this here. So we can check this. P of 0 should be equal to 100, and it is. After 16 months, I should have double what I started with. So good. And after 32 months, I should have 4 times what I started with. 32 over 16. This is 2 squared, so 400. So it checks out. So here's our model. I have my starting population, and then a term, or a factor rather, which governs doubling every 16 months. So this was A. Let's move on to B. What I want to know now is how many javelinas will there be after 6 years? So the first thing we want to do for this is to convert 6 years into 72 months. Then we just evaluate P of 72 is equal to 100 times 2 to the 72 over 16. So let's see here. So this is like 10 times 2 to the 9 over 2. So let's see here. 2 to the 4th is 16. 2 to the 5th is 32. So maybe 2 to the 9 halves is something like, I don't know, maybe like 25. So just approximating, this is something like 2,500 javelinas, which seems like a lot, right? But the point is, in that time period, they've increased by almost a factor of 32, right? So the population grows incredibly rapidly under these models. And now we can look at C, which is how long until 1,000. Well, I set 1,000 equals P of t, which is equal to 100 times 2 to the t over 16. So that tells me that 10 needs to be equal to 2 to the t over 16. So I've reduced my problem to solving a type of exponential equation. How do I solve such a thing? Well, we've studied this already. All I have to do is take the appropriate logarithm. So this tells me that log base 2 of 10 equals t over 16. So t is something like 16 times log base 2 of 10, which is, I don't know, maybe something like 50, since this is something like 3. Okay? So just to get an approximation here. In reality, we could use a calculator to get not exact, but a close to exact formula for log base 2 of 10. So this part C question required us to solve an exponential equation, but we knew how to do that. All we needed to do was take the appropriate logarithm and do a bit of algebra.